So in the previous lesson on moment of a force, we learned how to find the moment of a force in 2 dimensions. And then we said that the moment of a force is given by the magnitude of the force times the perpendicular distance from O to the line of action of the force. And then we said that moment is measured in Newton meter. Now in today's video, we are going to learn how to find the moment of a force in 3 dimensions. Now in 3 dimensions, it is very difficult to obtain the perpendicular distance, and so we are going to use a different approach or method, that is the cross product multiplication. So in 3 dimensions, the moment of a force is given by the cross product of R and then F, where R is said to be the position vector directed from O to any point on the line of action of F, and then F is said to be the force represented as a Cartesian vector. And so the moment of a force in 3 dimensions is given by the cross product of the position vector directed from O to any point on the line of action of F, and then the force F represented as a Cartesian vector. Now let's assume that we have a force acting along this line, and then we have a point O where we are going to take the moment about. Now the first thing we are going to do is to specify a position vector directed from O to any point on the line of action of F. And so we are going to treat this position vector as a sliding vector. Now you realize that this R is not perpendicular to the line of action of F, and so we define some distance, say D, which is perpendicular to the line of action of F. And then we also say that let the angle formed between R and then the line of action of F on this side be theta. Now in that case, then we have the perpendicular distance D to be equal to, since this angle is facing this side, then we say that D is equal to R times sine of the angle theta. And so since we have the perpendicular distance and the magnitude of the force, then we say that the moment about the point O is given as the force times the perpendicular distance. We have perpendicular distance to be R sine theta, so we have R sine theta times F, and that is equal to RF sine theta. So this is the moment of the force, and then we have the moment acting vertically upwards at O. So this is the moment at O. Now talking about the direction of the moment. The direction of the moment can be obtained by considering or applying the right hand rule. So let's assume that this is the right hand. So we have the fingers, and then we have the thumb, which is acting vertically upwards or acting perpendicular to the plane containing R and then F. Now if you want to curl the fingers of the right hand, you realize that you are going to move in the anti-clockwise direction. That is, you move from R towards F, and so you realize that the moment is in the anti-clockwise direction. Anti-clockwise direction. So the moment about the point O, which is given as the cross product of R and then F, has a direction which is in the anti-clockwise way. Now one important thing you need to take notice of is the fact that cross product is not commutative. That is, R cross F is not equal to F cross R. Therefore, the right order of the moment of the force, which is given as R cross F, should be maintained in order to obtain the right sense. So basically, this is the formula we are going to use to find the moment of a force in 3 dimensions as far as cross product multiplication is concerned. Now let's move on to the second item we want to discuss. So secondly, if a force is acting along this line, let's say we have a force which is acting along this line, the force F, and then we have this to be point O, and at point O, directed from O to any point on the line of action of F, we have the position vectors R1, R2, and then R3. And then let's assume that we have the moment acting vertically upwards here. Now, according to the principle of transmissibility, if you have more than one position vectors directed from O to any point on the line of action of a force, then the same moment will be produced at point O if you want to consider each of the position vectors. So what we are saying is that given more than one position vectors, if you want to find the moment of the force about the point O, then it is basically giving us, you can have the cross product of any of the position vectors and the force, and we are going to obtain the same moment. So MO is equal to, you can choose R1 cross F, and that will be the same as R2 cross F, and that will also be the same as R3 cross F. So whichever position vector you consider, be it R1, R2, and then R3, the cross product of any of these position vectors and F will produce the same moment. Lastly, if a body is acted upon by a system of forces, and then you want to find the resultant moment, the resultant moment of the forces can be determined by the vector addition of the moment of each of the forces. So let's assume that we have this to be the X, Y, Z plane. So this is the X axis, Y axis, and then the Z axis. And then we have a body which is acted upon by a system of forces. So we have this to be F1, we have F2, and then this is F3. We also have a point O, and then we have the position vectors directed from O to F1, F2, and then F3. So these are R1, R2, and then R3. Now, if you want to find the resultant moment acting on this body, then we say that the resultant moment is equal to the vector addition of the moment of each of the forces. And so we have the cross product of R1 and then F1 plus the cross product of R2 and then F2 plus the cross product of R3 and then F3. So basically, the resultant moment acting on the body is given as the summation of the position vector R times the force F, represented as a Cartesian vector. Now let's kindly take notice of the fact that moment does not always act in the anti-clockwise direction. Now let's assume that we have the right hand position such that we have these to be the 4 fingers, and then we have the thumb vertically downwards or acting vertically downwards. Now if you want to find the moment of a force or to take the moment, you realize that if you curl the fingers of the right hand, it's going to move in the clockwise direction. So this time we have the direction to be clockwise. So depending on where the thumb is facing, you can either have a clockwise moment or an anti-clockwise moment. So moment is not always anti-clockwise. It could be clockwise or anti-clockwise. Now, based on what we've studied so far, let's consider a few examples. Now, this happens to be our first question. Let's try this question. Determine the moment produced by the force F in the figure 414a about point O. Express the result as a Cartesian vector. Now, let's solve this problem together. So in this question, we have a force 2 kilonewtons, and the force is directed along the line AB, and therefore has a unit vector UAB. So we have F to be 2 kilonewtons, and then we want to find the moment about the point O. Now, if you want to find the moment about the point O, we know that the moment of a force about point O is given as the cross product of the position vector directed from O to any point on the line of action of F, and the force F represented as a Cartesian vector. Now, in this case, we are given the force F to be 2 kilonewtons. Hence, we need to represent the force F as a Cartesian vector, and that is given by the product of the magnitude of the force and the unit vector directed along the line of action of the force. Now, we know the magnitude of F. However, we don't know the unit vector UAB. So let's try to find the unit vector UAB. So the unit vector UAB is given as, now to find the unit vector UAB, we are going to move from point A to point B. Now, whenever you move from any point towards point O, then that is a negative value. You are going to obtain a negative value, and the moment you move from point O to any point, then you have a positive value. So basically, that is the information that you need to obtain. And so to move from point A to point B, it means that you are going to move along the X, Y, Z axis. So first, along the Z axis, you move from point A to point O. Now, since you are approaching point O, it means that you have a negative value. So that becomes negative 12. So negative 12k in meters. And then you need to move along the X axis. So away from point O means that you have a positive value, which is 4 meters. So that is 4i, also in meters. And then you need to move away from O along the Y axis, and that is also 12 meters. So you have 12j. Therefore, the unit vector UAB is equal to 4i plus 12j minus 12k, all divided by the square root of the sum of the squares of their coefficients. So you have 4 square plus 12 square plus negative 12 square. Now this is equal to 4i plus 12j minus 12k, all divided by, now when you simplify this, you are going to get 17.4356. So when you solve this, the denominator, you obtain 17.4356. Now let's further simplify. We have UAB to be equal to 4 divided by 17.4356 gives 0.2294 plus 12 divided by 17.4356, you have 0.6882j, and then minus, we have the same value, 0.6882, and then k. So this is the unit vector UAB, that is the unit vector in the direction of the force. Now let's move on to find the force as a Cartesian vector. So that is equal to, we have the magnitude of the force 2 kilonewtons times UAB, so times 0.2294I plus 0.6882 J minus 0.6882 K. So you multiply 2 across, and then you have 0.4588I plus 2 times this, you have 1.3764J minus 1.3764K, and this is in kilonewtons. So after finding the force F, or representing the force F as a Cartesian vector, we are left with the position vector. Now, according to the principle of transmissibility, to find the moment about a point, if you have more than one position vector, then any of the position vectors directed from O to any point on the line of action of the force produces the same moment. Now in this question, we can specify 2 position vectors. So one, we have position vector from O to A. So that is RA. And then secondly, we can as well specify a position vector from O to B. And that is called RB. So we can use the cross product of either RA and then F, or RB and then F. Since the position vectors are directed from O to any point on the line of action of F, it means that we are going to obtain the same value. So let's move on as we find the position vectors RA and then RB. So for RA, we are going to move from point O to A. And since we are moving away from O, it means that we are going to obtain a positive value. So we have 12K. So that is 12K in meters. So we have 12K in meters. And then for RB, we are going to move from point O to B. So first we need to move along the x-axis, that is 4 meters, and then along the y-axis, that is 12 meters. In all cases, we moved away from point O, which means that we are going to obtain a positive value. So we have 4I plus 12J. And notice that this is in meters. Now looking at the two values, you realize that RA looks more simpler, and so for the sake of this example, we are going to consider the moment to be the cross product of RA and then F. Now you can as well consider the cross product of RB and then F, and you realize that you are going to obtain the same value of moment. So let's try to find the moment of this force about the point O. And so we have the moment MO to be equal to the cross product of RA and F. And to find the moment, we are going to construct a determinant. That is a 3x3 determinant, where we have the first row to be the unit vectors I, J, and then K. And then for the second row, we have the coefficients of RA. So for RA, we have 12K, which means that the x component is 0, y component is also 0, and then we have the z component to be 12. Also for the force vector, we have the x component to be 0.4588, y component 1.3764, z component negative 1.3764. Now let's try to find the determinant of this 3x3 matrix, and that happens to be the moment of the force. So first of all, we select I, and then we cross the row and then the column containing I, and so we'll be left with 0, 12, 1.3764, negative 1.3764. So we are going to have I on the outside, so that is positive I, and then into brackets we have this value times 0, it becomes 0, minus 1.3764 times 12 gives 16.5168, and then minus j. So for the determinant, it's always plus minus plus, so minus j into brackets. So we select j and then we cancel the row and then column containing j, and so we are left with 0, 12, 0.4588, and then negative 1.3764. So we multiply this value by 0, and that is still 0, minus we multiply 0.4588 by 12, and then we obtain 5.5056 plus k. Also we select k, we cancel the row and column containing k, and then we multiply this value by 0, that is 0, minus this value also by 0, 0, and so we are going to simplify. So we have I times negative of this, that becomes negative 16.5168I, and then we have negative times negative, so that becomes positive, so positive 5.5056j, and then plus 0k. So plus 0k, we can choose to leave that out, and so in actual sense we can further simplify this as negative 16.5i plus 5.51g, and notice that this is in kilo newtons meter. So that's it for today's video. Thanks for watching, and see you in my next video. In the next video on moment of a force, we are going to solve 2 more examples. Bye bye.